Periodic trends are some of the easiest topics on the MCAT. Now, chances are you won't get a question that explicitly asks you about one, but will instead get a question that requires you to have knowledge of a trend in order to get to the right answer. There's sort of a shortcut method of learning the trends, which is to base everything off of ZF, effective nuclear charge, making that the only trend you need to remember. Now, I'm not really a fan of this method because that requires you to do a decent amount of reasoning when you're already doing a ton of reasoning on the MCAT itself. I'd much prefer spending the 5 extra minutes committing all the trends to memory so that I can just recall them on the test. It's really not all that much info. So to begin, I'll start with giving all credit to this periodic table to Wikipedia, which is where I got it. And with a few exceptions, most of these trends share similar directions, and that is they all increase from left to right across the group or row, and they all increase from bottom to top up the period or column. Now, first up is electronegativity, which is the pull or force an atom exerts on electrons in a bond. As you can see, it follows the rule and increases from left to right and from bottom to top. In my acidity video, I listed some useful electronegativities to know for the MCAT, which I won't repeat here. If you're interested, go watch that video. But these two are useful to help visualize the trend a little bit better. Fluorine, you should know, is 4.0. It's the most electronegative element. Cesium, conversely, is the least naturally occurring electronegative element at about 0.8. So you can see this trend a little bit easier with just these two values to map it out. Electron affinity is next. Now, electron affinity differs from electronegativity. Whereas electronegativity relates to a force on electrons by an atom, electron affinity is related to energy given off, read exothermic process, when an atom completes its octet. When the octet is completed, the atom exists in a much more stable state as a result of releasing that energy. So it's good to know that distinction, but on the MCAT, treat electron affinity just the same as you would electronegativity. Fluorine has the highest electron affinity, cesium has the lowest. Now, something else similar between electronegativity and electron affinity is that both trends end at the halogens. The noble gases are excluded. And this makes sense. The noble gases already have complete octets, so why would they want to exert a force on electrons? And they certainly can't give off any energy to form an octet because they're already there. They're already at an octet. Okay, ionization energy. It's the amount of energy required to kick off an electron to create an ion. It's pretty aptly named. Ionization energy follows the same trend, increasing from left to right and bottom to top. Now, there are different levels of ionization energy, the first ionization energy, second ionization energy, third, and so on. These correspond to the energy required to kick the first electron off, the second, the third, etc. And each level requires more energy than the one previous. Now, this trend does include the noble gases. They do have ionization energies. And as you might imagine, it would require a ton of energy to disrupt a complete octet. And as a result of this, the noble gases do have the highest ionization energies of any column. You can get that from the trend, but it just helps to remember said trend by thinking about it like that. Okay, next up is ZF, or effective nuclear charge, which is a measure of the net positive charge felt by valence electrons. The quick and dirty method of figuring out an atom's ZF is to subtract its non-valent shell electrons from the number of protons. Now, as a result, ZF does not follow the same trends. It only increases from left to right. And it pretty much stays the same down a period. It does vary a little as you go down the period, as the extra inner shells do have a slight effect on the net positive charge felt by the valence electrons, as those electrons get farther away as you go down the column, but for the most part, just treat every atom in the same period as having the same ZF. So short of doing some quick math, an even quicker and dirtier method is to just remember that the ZF of alkali metals is +1, of alkaline earth is +2, etc., etc. As I mentioned in the intro, all of the other trends can be figured out from this one, so if you're interested, I encourage you to read more on that, although I will discuss it for the next trend, atomic radius. So atomic radius follows the opposite trend as the others. It increases from right to left and from top to bottom. Given that the alkali metals have the lowest ZF, that is, the lowest net positive charge on its electrons, its valence electrons, that corresponds to a lesser electromagnetic force on said electrons, which means that the valence shell will be farther away from the nucleus. The alkaline earth metals have a slightly larger electromagnetic force, which draws those valence shell electrons in ever so slightly. It makes the valence shell just that much closer to the nucleus. And so ZF explains the trend in a group, across a row. In a period, as you go down the table, the atomic radius varies simply because there are more shells of electrons. And so as you go down the table, more and more shells equates to a larger atomic radius. Now for ionic radius, and you've probably been asked to rank ions based on their radii on a GenChem test before. Cations have smaller radii, while anions have larger. And it's an additive thing. A 2 plus cation is smaller than a 1 plus, a 3 plus smaller than a 2 plus, and vice versa. For anions, a 2 minus is larger than a 1 minus, and so on. And finally, acidity is the final trend in this video. Now, I discussed this much more in detail in my acidity video, but I'll touch on the basics here. Acidity doesn't follow the normal trend. It increases from left to right, yes, but also from top to bottom, not bottom to top. So it increases from left to right because more electronegative atoms have more acidic hydrogens bonded to them. Just compare HF to H2O to NH3 to CH4 to give you an idea. Obviously, hydrofluoric acid is more acidic than water, which is more acidic than ammonia, which is more acidic than methane. Now, acidity also increases from top to bottom because size matters. A comparison of the halogen acids shows that HI is the strongest and HF the weakest. The reason for this is that the conjugate bases all have the same amount of charge. It's just a charge of 1 electron in any case. The larger atoms can distribute that charge over a larger volume, thereby decreasing charge density. This increases the stability of the conjugate base, which correlates with increased acidity. So there you go. Here are a few questions. Some of these are short answer for a change. You won't get any short answer on the MCAT, but given that the point of this video is all about memorize the trends, it often helps to put things in your own words. So as always, pause the video here while you work on them, as the answer slide will appear in about 5 seconds, so pause it now. And here are the answers. Pause the video again if you'd like time to review, and if you have any questions or comments, feel free to post in the comment section of this video and I'll get back to you. So pretty straightforward stuff, no tricks or gimmicks, just straight up memorization, and I hope that was easy.